Okay, so now let's look at the algorithm. As I talked earlier, the algorithm is very simple. We just run a for loop, and we just have to handle the ith point in the sorted order of the list. So let's look at the first case where the point P is a normal point. So for example, this picture. What this means is that we don't have any fundamental change in the intervals that we have. So previously I had an interval like this that was sliding against this edge and this edge, and after hitting this normal point, suddenly this this interval is no longer sliding along that edge, so it's sliding against a new edge like this one over here. Okay, and I just need to reflect that. How do I do this? Well, so we assume that I have two edges, so I have ET here and I have E bottom here. So E bottom is a new edge, so I point to E bottom to the same interval because I just say that whatever E the top edge was pointing to, the bottom edge should also point to the same interval because there's no fundamental change in the interval list. Then I need to delete ET from the set of edges that intersect the sweep line, and I want to add EB as a set of edges that intersect the sweep line. And finally, for this interval, I want to remember that PI is the last vertex that I've seen so far along this boundary. Okay? And that's that. That's how I handle normal points. Now let's look at another case where the point PI is a top vertex of a point. How do I detect this? Well, the way I can detect a top event is that the point PI has both of its neighbors going downwards, but also point PI is outside the polygon. In other words, it's not inside in any of the intervals that I'm maintaining. To detect that, again, I could do a search into binary search tree along the vertices, along the line segment that intersect the sweep line, similar to how line segment intersection works. So essentially I could detect this. What happens in this case? In this case, I will have to create a new interval, right? Because as the sweep line moves downwards, this will create a new interval that is inside the polygon, at the sweep line. For this interval, I have two edges that bound it. So let's say I have two edges E1 and E2 that are adjacent to PI. For both of them, I could point them to interval I. I create a new interval. I set the interval of E1 is I and the interval of E2 is I. And finally, this interval remembers point PI as its lowest, as the last point that has seen before. Okay. And after that, I need to insert these two edges into the data structure that maintains the status of the sweep line. Again, so that was simple. What happens when you hit a bottom point? So in this case, this interval, after I hit this bottom, so sorry, actually the example is this one, right? After I hit this point PI, this interval that used to exist in my picture will disappear. Okay, so essentially I just delete everything. So I have edges E1 and E2. Both edges E1 and E2 need to be deleted. So delete E1 and E2, and also delete interval. So everything needs to be deleted, right? I just delete it. That's easy. Let's look at a merge vertex. What happens here, and the reason it's called a merge vertex is kind of easy to see, because two intervals will merge into one interval now. Okay, so let's look at the details of this. So let's assume that I have this PI is adjacent to two edges, E1 and E2. And by definition of merge, they both need to go up. And the way I can detect this event is that both neighbors go up, but also PI is inside the polygon. So then I know that I'm dealing with a merge point PI. In this case, before, E1 will be pointing to an interval, let's say I1, and E2 will be pointing to an interval I2. Okay? But after hitting this merge point, I need to delete I1 and I2, or I need to merge them into one big interval I. Okay. And I need to make sure that these two edges, instead of pointing to I1, they point to I. Okay. So therefore I need to update these two pointers. Right? So this edge also needs to point to interval I, that is the result of merging of these two intervals. And on top of that, this new interval should remember pi as its lowest point. Okay? So, and that's that. We're not going to ignore this comment, because this is what I'm going to cover. And also, right, the edges E1 and E2 need to be deleted from the start of the sweep line, because as the sweep line goes downwards, these two edges will no longer intersect the sweep line, so they need to be deleted. Finally, we look at split, and this is where we actually do something. What happens in this case? So if you hit a point pi where the neighbors are going downwards, but the point pi is inside the polygon, then you know that you're dealing with a split vertex. In this case, what's happening here is that it's essentially the opposite of a merge, right? So you have an interval that contains a point pi, and that's how we know point pi is inside, right? Because it's contained inside an interval. We add a line segment connecting pi to the lowest point that I've seen along this interval I. So remember that interval I has a field called p.lowest that points to the previous thing that I've seen along this boundary or before when I run the time backwards. When I run the time backwards, this is the lowest in this picture, but it could also be along the boundary, right? So for example, in this case, pi was remembered as the lowest along this, so which means that if you suddenly see a split vertex here, let's say like this, then that point will be connected to, say, pi. Okay, so connect this, make this connection. Based on, we're going to prove that in the exercise classes that this line segment is completely inside the polygon. So therefore it's a valid connection. So therefore it decomposes the the polygon into two smaller polygons. But on top of that, this connection will also remove pi as a split vertex. And the reason is the following. When I look at, say, the right hand side, this edge is going upwards by construction because I'm connecting pi to something that's above it. But by the definition of pi, the other vertex is below it. So therefore pi in this right hand side will turn into a normal vertex. One neighbor up, one neighbor down. Similarly on the left hand side, one neighbor up, the other neighbor down. So pi will be a normal vertex in both of these polygons. So therefore I'm getting rid of a split vertex here. So, and then the rest is essentially more bookkeeping stuff. This new interval is decomposed into two intervals, I1 and I2. I need to make sure that these edges are pointing to I2, these edges point to I1. And both of these edges remember pi as the lowest vertex that I've seen so far. And that's essentially that, right? And I also need to insert this edges E1 and E2 into the data structure that maintains the order along the sweep line. And that's essentially the entire algorithm. If you run through all of these cases, you'll see that every operation can be implemented on the binary search tree. So that's log n time per event point. So that's n log n time. But we also used a sorting step that is also n log n time. So therefore, this entire algorithm runs in n log n time. It gets rid of the split vertices, but it might not get rid of some of the merge vertices. And as I covered earlier, if you have some merge vertices left after this operation, you can just flip the polygon upside down and run the same algorithm again to get rid of the merge vertices as well. And once you've gotten rid of the merge and the split vertices, then you have essentially decomposed the polygon into a number of monotone polygons, so therefore we can run the linear time triangulation on them.